geometry and can make it entirely blue. So it's a parallel element, and it would lie within this constraint space, which is a bunch of basically disks that are parallel to each other and stacked. And if you drew a dashed line through their centers, that dashed line would be perpendicular to all those, okay? And it would achieve this freedom space, which is basically a rotation here along this dashed line and a translation, as well as every screw with every pitch in there. You imagine it stacked. It could bend, it could rotate, and it could translate like this as well, okay, and do any other pitch you'd like. Now, you have to be careful with this, because if I had generated this ruled surface of blue lines by translating and rotating with, you know, the same pitch that if you take the double derivative of with respect to the displacement, and it's constant, then it would be a hyperbolic paraboloid, and it would lie within this one. Okay, so just if you rotate those at a different rate as a hyperbolic paraboloid, you're going to get this one. Whether you go forward and then back like we did this one, it's clearer and it's a more symmetric element that's going to work better if you rotate this way and then stop here at this crease and then rotate back. Okay, but you didn't have to. You could have rotated it at a rate that's not consistent with. So anything that's not a hyperbolic paraboloid that rotates, you know, as it translates, will lie within this constraint space. Okay, and we'll have this freedom space. And we'll have an order of constraint, by the way, of 4 instead of 3, okay, like this hyperbolic paraboloid. Okay, so like I said, there's infinite ones of these. You can generate them all day. You can generate them for the rest of your life. But you have the complete fact chart, so you can generate whatever you need. And if you can 3D print them, then you can come up with designs that everyone's just totally blown away you're able to come up with, that no one could intuit or visualize, but that you know is correct because you're following the fact rules, okay? And that's just, I've just taught you how to generate parallel elements. We're going to teach you how to generate serial and hybrid elements as well. And so you can generate anything that's flexible at all, okay? And know how to analyze its constraint characteristics. Okay, so let's do an example here. Is this a parallel element? Well, first of all, you might say, oh, no, this is 2 parallel elements. First of all, it's giving you a hint here. It shows thatching down along this edge. So it's like the ground's there, which means the body's stuck. Stage attaches up here on this edge and on that edge. 2 stages join these two together. So you might look at this and say, no, that's 2 parallel elements. Those are, I recognize those 2 V blade flexures. Here's the V kind of blade flexure. I'm not sure they have a formal name, but let's just call them V blade flexures. You can say, oh, there's 2 of them. But I'd say, no, that's wrong. There's just 1 element because they're fused together right there and right there. Anytime 2 seemingly unique elements are fused together, they now count as 1 element, and this is a new element. Okay, so so that is, I think we can agree that that is 1 element. The question is it a parallel element? Well, I guess the answer is what you'd have to ask yourself is, can you draw blue lines that can connect the stage and the ground that pass entirely through the geometry without ever exiting it? And the answer is yes. Check it out. You could draw all these blue lines that connect the stage up here to the ground, pass entirely through it, and could you fill the entire geometry? Could every single nook and cranny of this be filled with blue lines so it's entirely blue? The answer is yes, and therefore it is a parallel element, okay? Okay, so then the next question is, which freedom constraint space does it possess, and what is its order of constraint? Okay, so we know it's a single element, we know it's a parallel element, and so what's its freedom constraint space? Well, one way you can find this out is, can you find all the red lines that intersect all the blue lines somewhere at least once? And you might stare at this for a while. I encourage you to actually put me on pause and try and figure out what the freedom space of this is, because this would not be, this would be a totally fair test question. But let's say you did that and you just want to know the answer. So you could imagine if I drew a red line down this line here, it would be, both line a plane, right? And they intersect at that line. So that red line will intersect all those blue lines somewhere at least once. Then another red line would be right through this point and that point. That would intersect all the blue lines somewhere at least once as well. And those are the only 2 red lines. So it's kind of like 2 orthogonal skew red lines, which if you look at the fact chart is, of course, the cylindroid. Here's your 2 They happen to be, they'd be the extreme generators too if they're orthogonal and skew. And so you'd have this freedom space with the two red lines on it and all the screws in between. Of course, this would be oriented like this. This is oriented how it is in the chart, but you'd have to take this and imagine orienting that with these two red lines. And then its constraint space is given to you like this. And of course, you'd have to orient this dashed line with these two lines as well. And you can kind of already see those are kind of disks within, it's like, right, it's basically these disks within the constraint space. Okay? And so what's its order of constraint? Well, you look it up, and this has 2 degrees of freedom. So 6 minus 2, this is 4. So it has an order of constraint of 4. Okay? Okay, so that's the intro to parallel flexure elements. Okay? Let's talk about now geometry sensitivity. Okay? So these are both wire flexures, technically. And the question is, well, you might look at this and be like, this is no wire flexure. This is like a big old fat post, right? Well, and you're right. This would not behave as a wire flexure either. And this, if this is the ground and that's the stage, and you join this, you'd instinctively know this is so big and fat and comparatively short to its diameter that this would totally lock this up at a constraint. It'd be totally exactly constrained. There would be no degrees of freedom on this guy, and you know that because you could draw, like what you do is you draw the blue lines that connect the ground to the stage that pass entirely through its geometry without exiting it, and fill it. So you could totally fill it entirely blue, and so sure enough, this is a parallel element. And sure enough, there's enough independent blue wrenches in there that it would be, right, let's, 0 degrees of freedom, so 6 independent wrenches in entirely filled blue space with no degree of freedom, okay, would be this guy. And so it would be locked up. It would be an order of constraint of 6. You wouldn't say it's over constrained because it's an element, okay, and it's a parallel element. It would be an order of constraint of 6, and this would be totally exactly constrained. This wouldn't be able to move. But if you look at this, there's only, you think, well, there's only one blue line that fits in it, and so its constraint space is here, and therefore its degree of freedom is here. So then the question becomes, is like, at what point, so as I shrink this diameter, at what point does it suddenly transition from no degrees of freedom to 5 degrees of freedom? Okay, and according to math, just if you just want to be super strict with math, then at all finite diameters, this has no degrees of freedom. It's you can draw 6 independent blue lines and an infinite number of redundant blue lines. So this would be fairly mathematically heavily over constrained, and it would always have no degrees of freedom until its diameter is shrunk to the point where it is infinitesimally small with no geometry in there, okay? And then at which point it would suddenly magically pop into from 0 degrees of freedom to 5 degrees of freedom and would be purely exactly constrained and no over constraint, right? According to the math. But of course that's absurd. There's reality. You can't ever make something infinitesimally small, and even if you could, it couldn't resist any load in tension or compression. Okay, and of course the thinner it gets, things buckle and stuff. But even in tension, if this was infinitely thin, it can't resist anything, right? And so when you add reality to the mix, you have to kind of interpret the math. The math is a guide, but it's very strict, right? You have to understand what the math is telling you. This is why it's not useful to consider any element as over constrained, because every element is over constrained, and that would be useless, right? Even this one with a finite thing has lines in it like this, and it's over constrained, right? And it would technically have 0 degrees of freedom, but that's absurd, right? So you have to look at things, and your eye, your brain, your common sense knows, okay, this is thin enough and long enough that even though it's finite thickness, we're going to assume this is a wire. It's going to behave like a wire, and it only has one blue line fit in it, and it has 5 degrees of freedom. Okay, and we're going to look at this and know this is 0 degrees of freedom is actually a structure. Okay, so fact doesn't do well with all its idealized things when it's at the intersection of different spaces. Okay, like you want to rush to the two extremes. You want this to be as thin and as long as possible, or you want this to be as thick and as short as possible to be considered 0 degrees of freedom. Okay, so rush to the extremes of what fact should be, and it will give you the better answers or better predictions of how things will behave. Okay, so let's look at other sensitivity things. Say I wanted you to design a parallel element that achieved these two translations and an orthogonal rotation. Okay, well, you'd say, okay, well, great, I know the freedom space is this. It's a box with a disk of translations, and I know its constraint space is this. Okay, so now take that constraint space. Can you visualize a geometry that can be filled, or that is connected to two rigid bodies that when you draw blue lines through the geometry can connect those two rigid bodies, pass entirely through the geometries, or the element's geometry without exiting it, and fill the entire thing blue, but use enough blue lines in there that there's at least three, there's three independent ones that you're using. So you don't just want to use a wire, right? Because that would work, that would satisfy all the conditions, but that's just one independent thing, right? And you wouldn't want to use two parallel wires, right? Two parallel blue lines, because that's also not independent. You need three that kind of aren't on the same plane. So what can you envision an element? Can you synthesize an element from what I've taught you? Put me on pause and think about this, okay? All right, so I'm going to give you an answer. Okay, there's, of course, infinite element geometries that would work, but one is just a hollow, infinitely thin cylinder. Okay, because if this is hollow and infinitely thin, and you connect the ground down here and the stage up on here, then you can find blue lines that can connect those two bodies and pass entirely through it without exiting it. These are the parallel lines. And they do lie within this constraint space. And there are at least three independent ones. They're not all on the same plane. And they can fill it, so the entire thing's blue. So it's a parallel element, and it lies within this constraint space. Okay. Now, of course, the thinness of this has to be infinitely thin, which is, of course, impossible. But if it's super, super thin, it will mimic that constraint space, and therefore will achieve this freedom space. Okay? And that might be not terribly intuitive, but trust me, if you CAD this and put two giant blocks, sandwich it on there, the first three mode shapes will be the two translations and the rotation down its axis. Okay? And then the fourth motion will be a mode shape associated with a natural frequency that may not be much larger than the third, but will definitely be in that order. Okay? And again, you could change the order of those and do fancy, disturbing things by changing the shape of those stages without touching even the element, which is, again, why I don't like definition degrees of freedom from a modal analysis standpoint. But it's still useful. Okay? But notice here, as far as sensitivity of this, say I make the diameter of this cylinder smaller and smaller and smaller, at some point it'll just behave as a wire, right? And that's the point where where it's infinitely small, which can never be achieved. But in reality, if this diameter gets smaller and smaller and smaller and smaller, it behaves as a wire. And also in reality, the bigger and bigger and bigger it gets, and the shorter and shorter it gets, well, now you can actually, if there's any finite thickness at all, which there always has to be, you can actually start fitting lines angled, right? If this became infinitely large diameter, then this would be a plane, and you could easily, even if that was infinitely thin, if the diameter of this cylinder was literally infinitely large, it would be a plane, and you could easily fit lots of different blue lines in here on that thing's plane. Okay, but of course in reality you can't get the diameter infinitely large. You can get it really large though, and of course in reality you can't make this infinitely thin shell, and so in reality you do get extra blue lines through there, and that would stiffen it so that it gets no degrees of freedom. Okay, so depending on how you sweep this, depending on how thin you make this shell and how small you make the radius or diameter, you could make it act like a wire flexure. You could make it act like this degrees of freedom, like a cylinder, or you could make it act like it has no degrees of freedom. And if you join this side to that side on top, nothing will move. Everything will be locked up. It'll be a structure. Okay? So, and you might ask, well, at what point does it transition to those? Well, it's very gray in reality. And the math doesn't guide you because the math is all heavily idealized. And so you have to just kind of use your intuition and rush to the two extremes. You know, when this is super, super thin, you say, okay, it's going to be a wire. When it's about this, it's like, you know, it's about that. And when it's large enough, then it's basically no degrees of freedom. Okay? And you can start quantitatively putting numbers on this if you put the same size bodies on both sides and do the modal analysis and see what natural frequencies come in what orders and that kind of thing. That can put... The nice thing I do like about modal analysis, degrees of freedom, is it takes reality into account, removes all the idealized stuff, and you can actually start ordering, you know, rank ordering your natural frequencies and mode shapes. But again, like where do you decide to cut off what things are degrees of freedom, what things are constrained? At that point, is not clear. So there's a lot of ambiguity in all the definitions of degrees of freedom. But I think fact is the least ambiguous and the most clear because it's all idealized. But again, it's not going to mimic reality all the time, and and you have to. I mean, just use it as a tool to when you're shaping and designing these things. You rush away from you rush to the extremes, right? Make them super thin, and make it so it's going to work with the freedom spaces and constraint spaces. So. One trick you can do if you want to have a really thin vessel that has a large diameter here, you know, inside the cylinder, but still exhibit this freedom space you want, is you could kind of corrugate the outside of it. And why would you do that? Well, because the more curvature any point along the outside gets, the less you can put angled blue lines in there, right? So the larger the radius of this got, the less curvature this cylinder has, and to the point where if it's infinitely large, it doesn't have any curvature. It's just a flat sheet. And the flatter and flatter it gets, the more angled you can put these in, the more they can resist, you know, degrees of freedom that you want. You don't want them to resist. And so if you put all this corrugated stuff in there, then you up the curvature at every point along here, and you ensure that only the blue parallel lines go in, no angled lines. And then you can get the radius of this to be as large as you want, and this to be as short as you want, within reason, of course. And then you can get the freedom space you wanted. So this one would nicely achieve the two translations and the rotation, okay, or at least more nicely with cleaner modal analysis, mode shapes. Where the first three natural frequencies correspond with mode shapes that you'd want, and the fourth natural frequency is much larger. Okay, and again, by understanding these principles of fact, you can push those natural frequencies away and make decisions without even doing modal analysis. You can analyze things and design things intelligently. Okay. Okay. By the way, another definition of degrees of freedom. So there's actually three definitions of degrees of freedom. There's the fact definition, which is just the independent twists within freedom spaces, or the degrees of freedom. That's one definition. Another definition is the lowest natural frequencies, the mode shapes corresponding to the lowest natural frequencies. But again, you know, the cutoff between when it's a natural frequency and not is very ambiguous with that definition. But the third definition of natural frequencies is just comparing directions of stiffness quantitatively. But of course, that's very difficult to do because there's four different kinds of stiffnesses. There's force to displacement, there's force to angle, and then there's torque to angle, and then torque to displacement. And those are the four different kinds of stiffnesses you can get, and they all have different units, right? And so, you know, it's difficult to even compare them because you're comparing apples with oranges. completely different quantities, and then again, it's like who says how much larger does this one stiffness need to be than another stiffness in another direction to be considered constrained versus not constrained, and so that's just as wishy-washy. So no one really has rigorous definitions of degrees of freedom when it comes to compliant systems, but all three definitions are kind of useful to think about, to try and constrain certain directions as much as possible while allowing high compliance and low constraint other directions as much as possible. Okay, but I find FACT to be by far the most useful, and then verified using modal analysis. The other definition is almost useless because it's, like I said, it's like comparing apples with oranges. They're not even the same units. Okay. Okay, so that's a little tangent. Okay. Okay, so but this geometry sensitivity topic was hopefully to show you that reality gets gray. It's not as idealized and nice, and freedom and constraint spaces can be sensitive, and be careful. Okay. Okay, so let's look at just very quickly elements that don't satisfy the parallel condition. So at this point, you might say, well, it seems like every geometry you've drawn and every geometry that can be generated from the fact chart, is parallel. You can always draw blue lines that connect their bodies without ever exiting their geometry, and they can fill the entire thing. Show us something that's not parallel. Well, I've hinted to things. But here's two good examples, okay? So here you can see this whole thing is a compliant thing. It's got a little notch cut. It's like basically a blade with notch cut in it, the side, okay? This is, by the way, a very clever element that people use to not over-constrain parallel guide mechanisms. We'll talk about that in a second. But anyway, the point is, that's an element that deforms over its entire geometry. It connects two rigid bodies here as shown on this end and this end. And so it's showing you and by the way, this is why I don't, remember, I every time I draw elements, you can't just give the element, you have to kind of show the two ends that it connects the rigid bodies. That's why I show rigid bodies in some of them, to make it clear what two ends it joins, because that very much affects whether it's a parallel, serial, or hybrid element in many situations, as I've given examples of. But in the diagrams, you wouldn't draw these as rigid bodies because you're just looking at the element. You draw those points, lines, or curves. But anyway, we'll get to that a little bit later. But anyway, here is an element. So ask yourself, is this parallel? Well, you might say, well, no, it's obviously a blade flexure stacked in series with a nub flexure stacked in series with another blade flexure. So you can obviously see it's three parallel elements stacked in series. That should be one clue, but don't follow that clue. Ask yourself if it fits the parallel condition. Okay, that's a much safer way to do it. And the parallel condition, there's two things, right? Can you find blue lines that connect these two rigid bodies and pass entirely through the geometry of this? Well, yes, you can. See, here's a blue line that connects the two bodies, never exits this geometry at any point, and directly connects it. That works, okay? Well, what about the second condition? Are there enough blue lines that can fill the entire geometry? The answer is no, right? You can fill this entire geometry. All this stuff could be colored pure blue, and this stuff could be colored pure blue. But what about this zone right here? You will never find a blue line that connects that rigid body with that rigid body, pass entirely through the element without exiting its geometry, that will be in that free zone, or this zone, or this zone, or this zone, those four free zones. You can't do it. And as a consequence, this is inherently not a parallel element. Okay? Now you can say, well, that's silly. Like, what if I just took a chainsaw and cut these corners off? Right? Cut off these four corners so it did satisfy the parallel condition. Well, in that case, you're right. It would become a parallel element. It would become that V parallel blade, or that V blade thing that we looked at earlier. And that is a parallel element. But this thing, just because of its four corners, is not, because it doesn't satisfy that condition. And you might think, well, this is silly because it behaves with the exact same kinematics. It has the exact same freedom space as the V blade thing. And so why the distinction? Well, I will show you examples where for silly reasons like this, if it doesn't satisfy the condition, you can't analyze it anymore using the same parallel rules. Okay, you'll get different freedom spaces. Okay, so you'll just have to trust me on that at this point. But basically what you do is you apply the two parallel conditions to an element. If it satisfies it, you know it's parallel, and you can analyze it as I've taught you in this, and design it as I've taught you in this. If it breaks any of the conditions, like there's free zones here, or like this one, there isn't even a single blue line that connects this rigid body with that rigid body that passes through the geometry without exiting it. Okay, it would have to exit this and go through air essentially to hit this stage, and the stage would have to be larger, right? And so this you know, there's not even a single blue one that works, let alone all the free regions in here that couldn't be achieved. So this one definitely could not satisfy the parallel conditions, not even one of them. And so if a parallel, or if an element doesn't satisfy one or both of the parallel element conditions, it is not a parallel element, and do not analyze or design it using the rules I've taught you in this lecture. It is at your peril. You might get a freedom space that's correct, luckily, but there are many that will give you the wrong freedom space. Okay, I will be teaching you how to do this in a later lecture, how to analyze serial or hybrid elements. These are both serial, by the way, as that says. Okay. Okay, so that's that section. So that tells you what parallel elements aren't. Okay. This, by the way, is like, you could think of as a bunch of parallel blades stacked in series, right? Okay, and this, like I said, you can think of it as a parallel blade, a nub flexure, and a parallel blade. And of course, a nub flexure is parallel. So 3 parallel elements stacked in series. Okay? But again, don't necessarily think of them that way. Okay? But I'll be talking about this in later lectures. Okay, so let's do an exercise here. Remember we went through all the examples in a previous lecture about how to synthesize parallel micromirrors that achieve tip and tilt, and then we did tip, tilt, and piston. But like the previous example, we tried just tip and tilt, and we went through all the possible constraint spaces to design a parallel system that achieves just tip and tilt. Except back in those days, we were constrained to only use wires and blades. Now we can use a much larger library of parallel elements to design a parallel system that has just 2 rigid bodies that are connected directly to each other by parallel elements, and that achieves tip and tilt. Okay, so that's what it's asking. Let's synthesize an exactly constrained parallel flexure system that achieves tip tilt degrees of freedom only, but uses at least one nub flexure as shown below. Okay, that's the nub flexure. By the way, you're now prepared to understand the highest definition of what a parallel system is. A parallel system, flexure system, consists of 2 rigid bodies connected directly to each other by parallel elements. Okay? And this is where a lot of people disagree with me. I see lots of flexure systems where they have serial elements arranged in parallel and just 2 rigid bodies. And they say, oh, that's a parallel system. And it's like, well, you might think it is, but according to fact won't work if you call it such. Fact only works, the rules of fact only work if you call parallel systems 2 rigid bodies connected directly to each other by parallel elements. And those elements are going to always be arranged in parallel, right? Okay? And so, where the stage, they all experience the same twist, or displacement twist instead of the same wrench. Okay. All right. So that's what the most rigorous definition of a parallel system is it's got to consist of parallel elements. Okay. Okay. So let's do this example here. So remember, say we want our micromirror to just do tip and tilt. Remember, we look up in the 2DOF column. Here's its constraint space. Okay, we know we have, this has 2 things in it, that has 4, so we have to pick 4 things. And remember, so, here's all the motions you get. You don't just get the tip and tilt, you get all the things in the disk. Here's the constraint space, it's got 4 things in it. Okay, and remember, we said there's 4 ways you can pick your 4 constraints. meaning there's 4 subconstraint spaces coincidentally for this guy. You can do 3 from the sphere, 1 from the plane, 2 from the plane, 2 from the sphere.